I will talk to you today about the clash between the theory and practice of deep learning. And in order to put it in the correct context, let's move back about 13 years ago to 2011. So the president was Obama, and the greatest problems we had here in Israel were the prices of the cheese. And at that time, I started my PhD. And I want to describe you the way learning theorists, or at least myself, view machine learning at that time. So the dominant methods in practice were linear methods. These were methods that optimized over a linear class of predictors or a convex subset of such a class. So two prominent examples are support vector machines, SVM, and AdaBoost. And we sort of understood these methods. We understood why the optimization algorithms finds good solution, because they optimized over a convex optimization problem. We sort of understand why these algorithms were able to generalize on out-of-sample examples. And in light of that, the main role of the theoreticians, or at least the way I view this, was the following. One role was to develop a faster algorithm, faster implementation for these linear classes. Another role was to extend the capabilities of these methods to more domains and to more problems and to solve them. And another thing which I focused during my PhD is to prove results that explains why we cannot do anything better than these methods. Now, moving forward 4 years to 2015, this is the year when I finished my PhD. So at that time, deep learning took over almost every part of machine learning, and it became the dominant methods in virtually all domains of machine learning, and it was clear that it is here to stay. And from a learning theorist perspective, this essentially shatters everything we believed in, everything we thought was true. So in particular, we saw that algorithms are able to optimize over deep models, despite this should be a very hard task from a computational perspective. We showed that neural networks are able to generalize on out-of-sample examples, despite they have billions of parameters, much more than the number of examples. And we needed, it was clear that we need a dramatic change in learning theory. So the question I want to discuss today is whether we can have some time machine and go back in time to 2011. That is, whether a theory can go back and explain the practice of deep learning and even support it in the sense of developing new algorithms. So I will try to elucidate two of the main gaps we need to close in order to do so, and survey a little bit about the progress that's been made over the years. Okay, so let's start by fixing the algorithm. So to stay focused, we'll consider a relatively simple and standard algorithm for a neural network optimization. So we'll consider a fully connected network. We'll denote the loss on the sample loss by LS of W. This is the average loss on the sample if the network weights are W, and we'll similarly denote the population loss, the loss on the distribution, by LD of W. We'll assume that the inputs are normalized so that each coordinate is between -1 and 1, and the input dimension, the dimension of the inputs of the network is D. We consider a simple architecture, fully connected architecture. For simplicity, we'll assume that the width of all layers is the same. We have D neurons in each layer, and the activation is the standard ReLU activation. And we'll also consider the most standard stochastic gradient descent algorithm. And this algorithm starts from Javier initialization, all the weights are initialized independently, and they are Gaussians with mean 0 and variance 1 over d. This is, I think, the most basic initialization of neural network weights. And after this initialization, for capital T steps, we'll make a stochastic gradient step. We'll sample some mini batch. We'll compute an estimation of the gradient based on this mini batch, multiply it by some small number eta, and subtract it from the current weight. Okay, so this is just a stochastic version of gradient descent. Okay, so let me discuss a few things that we don't understand about this algorithm that works so well in practice. The first thing is generalization. How come the population loss is close to the sample loss, even though the number of examples is much smaller than the number of parameters? And one of the prominent ways that we try to explain it is via the notion of implicit bias. So we try to show that in some way the algorithm the stochastic gradient descent algorithm prefer simple solutions. And there are many ways to formulate what simple means. So one way is that the function that we learn is some maximal margin solution in some sense. Another way to formulate simple is that the weights that we've learned are close to the initial weight. Okay, so this makes sense if we don't do too many steps, or if we add some regularization that encourage the weights to be close to the initial ones. And I want to discuss in a bit more detail about the second condition. So a natural conjecture based on what we know from the linear case, from linear classifier, is that the empirical loss is the population loss is upper bounded by the sample loss plus a small quantity, which is this distance multiplied by the square root of the dimension over the number of examples. So if this conjecture is true, this can explain, at least in some cases, why neural networks generalize on out-of-sample examples. And let me shortly survey our progress on this conjecture. So in 2002, many years before the new wave of neural network, this conjecture was shown true for neural network of depth 2. And in the last decade, in light of the development in practice, people tried to generalize it to a deeper network. And we were able to do that with somewhat inferior parameters if we replace the input dimension with the input dimension square. So this gives a weaker explanation to generalization. It's not clear that it can explain generalization with less examples than parameter, but still it is a progress toward proving this conjecture. And later we were able to prove this conjecture in full, but not for the radio activation, but rather for a smooth version of it. And the conjecture in full is still open, and still several people try to prove it. Another prominent gap between theory and practice is the ability of stochastic gradient descent to find good solution. So we know that optimizing a neural network, finding the best weight for a neural network is a very hard problem from a computational perspective. We know that even if we're guaranteed that there are weights with zero loss, then it is NP hard to find weights that are even slightly better than trivial. From another perspective, what SGD is doing is optimization on a highly non-convex landscape, so it's not at all clear why it can find good solution. And in order to discuss this question in a bit more depth, let me make a very quick survey of 30 years of research in computational learning theory. So 40 years ago, Turing literate Leslie Variant asked what functions or what classes of functions are learnable in polynomial time. And today we can roughly answer this question. We can roughly say that unless we see some breakthrough, the best we can do is to learn linear classes of function. And the prominent examples of such classes are linear predictors and more generally constant degree polynomials. So one thing we can ask is, does SGD on neural network learn polynomials? That is, if the function, the target function that we're trying to learn is a polynomial or can be well approximated by a polynomial, can we prove that SGD will find a good solution? Okay, so this doesn't contradict any known hardness results. So we can try to answer this question. Okay, so this question is a bit strange because we're optimizing over a neural net, so why do we care about polynomials where we have other algorithms that learn it? So let me tell you two things about this. So one thing is that if we will be able to show that SGD can learn constant degree polynomials, we'll at least be in a position where we know that SGD on neural network is at least as good as linear methods that were prominent 10 years ago. So this is some progress. This is not everything we want to show, but it is some progress. On the other hand, this will not explain why SGD on neural network is better than these methods, but still this is a decent step forward. So let me tell you a little bit about the progress on this question. So here is a conjecture that we can make. We consider polynomials, and we want to show learnability of polynomials whose coefficient vector has norm at most m. And we can conjecture that such polynomials can be learned by SGD on neural network with m-squared parameters. Okay, so there is a reason why we have m-squared parameters. We know that smaller networks cannot perform this task, and we expect that network of size m-squared will be able to learn this class of polynomials. And this is what we were able to show. About a decade ago, we were able to show that network of polynomial size polynomial in M can learn these polynomials, but this polynomial was very large. It was, I think, M to the 24, and over the years, we got better and better polynomial dependency, but still not M square. What we can show for M square is that a variant of stochastic, non-standard variant of stochastic gradient descent can learn this class of polynomials using network of size m squared. But again, the conjecture in full remains open, and we're still working on it. Okay, what about moving beyond linear models? So as I told you before, showing learnability of polynomials will not explain the benefits of depth, will not explain why neural networks are better than linear methods. And in order to do so, we'll need to show results beyond polynomials. And there are fortunately, there are only few results of this type, and most of them are on relatively toy models. And the major challenge here is just to find the correct conjecture. So as opposed to the previous gap I've mentioned, where we could state clear conjecture and we made some progress towards proving those conjectures, here we don't even know what the correct conjecture is. And a big challenge and a big breakthrough would be to finding a reasonable conjecture. And let me say that if we will find such a conjecture, maybe it will come with new deep learning algorithms. And the reason for that is that in order to find such a conjecture, we'll need to find a class of models that is deep in some sense and is efficiently learnable. And probably in order to show that it's efficiently learnable, we'll show that some algorithms can learn it. And probably, at least in the beginning, it won't be SGD on neural network. And it will be interesting to see how these algorithms, they can, in some sense, replace neural networks. Okay, so let me summarize. Can we go back to 2011? Can theory go back and explain neural network practice and maybe even be the engine behind new algorithms? So there is steady progress in explaining generalization and in showing that neural networks at least can learn models that we know that are learnable. So we know where we're going, we have some conjecture, and we make progress towards proving them. Regarding the role of depth, here we need a breakthrough in order to continue, and we might get it or not. That's it.
Thank you, Amit.
Thank you.
Questions to the speaker?
Yes.
So this is a field that is newer to me. So my question might be basic, but I just wanted to understand. When you talk about optimizing the neural network, you're really talking about finding like the best model for whatever data that you have.
Yes.
So you're saying that it's NP hard to do that, which is why people don't do that. But yet, when people sit and they do research or they do work, you know, sometimes you do linear models, but sometimes you use the neural network. So in practice, when you use whatever neural network package that you have in MATLAB, that you have in Python, what are you doing? And why does it matter that the optimization is NP hard when you do it in real time?
Okay, so the question is what algorithms do in practice given that this problem is NP hard. So what the algorithms are doing is SGDs, gradient descent, which is a heuristic. It's an algorithm that does something, produces some solution, but there is no guarantee that this solution is the best network. In practice, in many cases, it is the best network or it is close to the best network, but the point is that there is no guarantee.
Like the theory doesn't line up.
Yes.
Okay, thank you.
Any other questions? So I'll ask one question. What can you say about adversarial examples?
Okay, so another phenomenon that is apparent in recent years is adversarial example, where we can have an example, for example, if we do image recognition, we can have a picture which is a dog, and the neural network classify it as a dog correctly, and an adversary perturb it a little bit, and it's still, human cannot tell the difference, but the network says that now it's not a dog, it's, I don't know, a chair. And the question is, can theory explain that? And this is, again, an area where there is some progress, and we are able to give explanation in some cases to prove that there must be an adversarial example. It's still a challenge to find scenarios where we can avoid these adversarial examples.
If you would allow me to conjecture for a moment a solution to the problem you asked on why neural nets work so deeply well, particularly as we layer them, perhaps it's because they build a complex adaptive system of complex adaptive systems that's simply recursive and self-organizing, and then through its interaction set emerges new phenomenon and new capacity. As from the literature on complex adaptive systems, we know such models can do. In other words, it's a self-organizing system. I'm sorry, I'm repeating the same word, but that's, you know, the term.
Yeah, so I think that this is one avenue how to explain it. Maybe to show that, I mean, this is maybe another notion of simplicity of what we want to learn that can explain why these neural networks are so successful.
Okay, so if there are no more questions, let's thank the speaker. And this concludes our session.